Hello students. After completing the interference topic in our optics unit, now we are going to come to next major heading, that is diffraction of light. Okay, so this is another optical phenomena which we need to understand. So let us understand its definition. The bending of light at sharp corners and entering into the geometrical shadow region is called diffraction. So students, one bending of light we have already understood, where the two mediums were there. So if the light ray enters from rarer to denser or denser to rarer, then its path gets bent. In the same manner, like the refraction we did, one phenomena where due to the medium change, the bending takes place. So in the same manner, we have another bending of light. We know that light travels in the straight line, but somewhere the bendings take place. So where the bending of light take place other than the change of medium, so that is at the sharp edges or sharp corners. And what is the meaning of this GSR? Let us understand it with the help of the diagram. Now we have here two diagrams. Okay, in both the diagrams we will understand the diffraction phenomena. Okay, so first of all, this side diagram is slit concept. You already know the slit concept. So this is our source, this is slit, and this is the screen. So as we know, triple S arrangement is there. So S, source, slit and screen. So this is the slit concept. Slit means the device which allows the light. Okay, so here whatever opening is given, from this opening the light can move further. Okay, and now in the second diagram we have the source, and this concept is that this is the obstacle. Okay, a small obstacle is kept, and what we will see on the screen. Okay, so last one is the screen. Let's understand first diagram. What is the idea? First of all, the source of light will generate the light, and then here the slit is the one which will allow the light. So here some part of the screen will be illuminated with the light. The light will come, and from this allowed path the light will come and it will reach on the screen. So this part of the screen, if I name it AB, so AB is that part where the light is present, and where the light is not present, we call these regions what? GSR, geometrical shadow region. So here also GSR is present, and here also GSR is present. So GSR is present on both the sides of the screen. So geometrical shadow region. Now what is diffraction? See, till now we have traveled the light in the straight line path. Now what happens if these edges of the slits are very sharp? I'll draw the microscopic view. Suppose the edges of the slits are very sharp. Okay, so what will happen? As the light will reach here, then here at the sharp edges of the slit, the light will bend into the geometrical shadow region. Okay, it will bend, and where it will go? It will go where it was not supposed to go. So in the geometrical shadow region it will enter. This way it will enter into the geometrical shadow region, both sides. Here also if the sharp edge of the slit is there, it will bend. So this bending of light is called what? Diffraction. So just assume, just see in the diagram, carefully understand. The light travels in the straight line path, but when the light is traveling, if it encounters any sharp edge or sharp corner, then it will bend, and it will bend where it will go? This side or this side. So it will enter into the geometrical shadow region. So this is the concept of diffraction. Now let us understand it with the help of an obstacle. So obstacle is just opposite to the slit. Slit is the one which allows the light. Obstacle is the device which does not allow the light. So when the light will come from the source, because of this obstacle, the light will go, and this part will become the geometrical shadow region. You can see in the diagram, this is the obstacle, this is the source. So obstacle is that which does not allow the light to move. So when the light will start moving from the source, here on the screen the shadow of this obstacle will be formed. So where the light is present, so in all these areas, here the light is present, here the light is present, and because of the obstacle, okay, or opaque object, the light is not present here. So this is called shadow region. Okay, now where the diffraction will start? So just understand, if the obstacle corners are also sharp, these obstacle corners are sharp. If I draw, it should be this way. The sharp edges should be there. Then the light will bend. Okay, so original path of the light should be the straight line, but it will bend here and it will enter where it was not present before. So here already the light is present. Here shadow is there, so light will enter into these regions. The diagram now. Because of the sharp edges, the light came and bent. Okay, and it entered into the geometrical shadow region. So these two diagrams are explaining the diffraction, and we are saying that bending of the light takes place everywhere at the sharp edges. So what is the definition of that sharp edge? So the condition of the diffraction is that whatever is the wavelength of the light, of that same order, the size of corner of obstacle should be. Okay, so this is the important condition which is required for the diffraction. Wavelength of the light is in nanometers. So the diffraction gratings, that means all these diffraction devices, should also be, their sizes should also be in nanometers. That means 10 raised to power minus 9 meter order they should be. Okay, overall this condition you have to remember. Now, like we have completed in the interference chapter, the Young's double slit experiment. And with the help of that experiment setup, we have found out the conditions of maximas, minimas, with the help of superposition principle and fringe width. In the same manner, in our diffraction topic also, as we have said that whenever the light comes at the sharp edges, then the light enters into the geometrical shadow region. So why does it happen that it enters into that region? That we will understand with the help of wavelets concept. And also, like in interference pattern, means on the screen we get maximas and minimas. In the same manner, in the diffraction also, we are going to get maximas and minimas. The pattern will be little different. So let us understand now the setup. Okay, so as we already have triple S arrangement, this is the source, this is the slit. Now in the Young's experiment, we have taken double slit. S1 and S2 we had taken. But now in the diffraction, and which diffraction we are doing? Fraunhoffer diffraction at a single slit. So now there will be only one slit. Okay, as we have discussed already diffraction, that in the diffraction source and one single slit will be present and one screen will be present. Now from the source, the center in front of the source, the screen's point is called center of the screen, and again the datas are the same. This is called capital D, the distance between the slit and the screen, and now there are no two slits, there is a single slit. So this single slit's width is called small d now. Okay, this width of the slit is called small d. We can name the slit as AB. Now what we have to do here, first of all, here we have to find out the conditions of maximas and minimas. So why the maximas minimas will be obtained? Because diffraction is almost similar to interference, so that's why this comparison is written. In the interference we have two waves. Okay, so in the interference, it is the superposition of waves from two current sources. S1 and S2 were two slits, and from that two slits we get two waves, and we do the superposition of that two waves, and as a result of superposition we get maxima minima. In the same manner, diffraction. In the diffraction you can see there is a single source, only one slit is present, so single source is there. But according to Huygens principle, each source or this wavefront we can divide into number of wavelets, and now superposition of wavelets will be done. Okay, so what is diffraction? It is the superposition of two wavelets from the same source. Okay, so the problem is not there. In the interference there are two sources, so two waves coming and superposition takes place in interference. But in diffraction there is only one source, and it is also point source. I have drawn it broader because to show some data, otherwise it is very narrow slit. So there is only one slit, means one source is there. Now how do we make the superposition? So superposition is done between the wavelets generated by the single source. Wavelets can be generated more. So between the wavelets we do the superposition. Okay, and the conclusions of interference are only taken here, that if the effective part difference between the wavelets is 0, then we get the maxima. So let us start doing our first question, conditions of maxima and minima. Conditions of maxima and minima. So this will be the first question. It will be a 3 or 5 mark question. It will be there in the board paper. And the second question of diffraction will also be calculation of fringe width, as we have done in our interference topic. Okay, so let us start this question. First of all, with the help of this diagram, we will talk about center. What we will obtain on the center, will it be maxima or minima? So you can see here it is a slit, and this slit is illuminated by the light. So light is present here, but the light is present in form of maximas and minimas. Distribution takes place. So how it happens, let us start. First of all, the light will come and it will be reaching at the AB slit. So here light is present. Now we will divide this slit into two parts. AP and BP, which are equal sized parts. Okay, these are equal sized parts. Now we will take the wavelets starting from A point and wavelet starting from B point. Okay, so they will travel and they will reach at the center of the screen, because we are just now talking about center of screen. So the wavelet starting from A to O and wavelet from B to O, they are traveling equal distance. Okay, they are traveling equal distance. That's why the path difference between them is 0. And according to our interference conclusions, whenever the path difference between two wavelets is 0, then we get the maxima. Now as we have divided the slit into two parts, so what we have to do, we can divide the first upper half of the slit into number of such positions and lower part also, like that. We can take the second wave starting just near A, and we can take another wavelet starting just near B point. Now these two waves also will travel equal distance, so again maxima will be obtained. So this way, whatever number of wavelets are starting from upper part of the screen, upper part of the slit, corresponding to that, all the wavelets which are starting from the lower part of the slit, they all travel equal distance. That's why the path difference is 0. So we will get the maxima. So let us write this answer at least for the center. You have to give the language. At the center of the screen, what we will obtain? So wavelets from the upper half of the slit AB and lower half of the slit AB travel equal distance. So effective path difference 0. So we get central maxima. So this is the proof that we get at the center maxima. Now we have to discuss about any random position on the screen. Let us start. Note down. Okay. After discussing about center of the screen, now we have to take any random point P1 on the screen. Okay, so at point P1 on the screen, what will happen, that we are going to discuss with the help of the same diagram. Okay, so for P1 you have to draw another diagram. Second diagram is this. Let us start now. So what will happen? First of all, let us draw the waves reaching from A1 to P1 and B1 to P1. A to P1 is lesser distance and B to P1 is greater distance. That means you can say that BP1 is greater. So what is the path difference between the two waves that we need to calculate here? So for drawing the path, for calculating the path difference, we draw a normal. Okay, we draw a normal on this line. So let us call it N point. Now how to calculate this BN path difference? Our path difference is coming here BN. Okay, so since we have already discussed that this AB, this is D, small d, this AB distance is small d, and if this is theta coming, okay, so how it will be, this will come d sine theta. Okay, you can see it from the right side triangle. BN means perpendicular, so if I tell you the calculation, Bn upon hypotenuse AB is equal to sine theta. So Bn equal to AB sine theta. AB means D. That's why this path difference will come D sine theta. Okay. This distance is capital D, and whatever random fringe we have taken on the screen, suppose it is nth fringe, so its displacement from the center of the screen is yn. Also, this center of the AB slit we have to join with P1. This angle is of the center point is theta with P1. Okay. Now the path difference has come, Bn means D sine theta. So to find out what we will obtain on the screen at point P1, we have to assume some values of D sine theta one by one, and after that we will start dividing the slit into parts. So first of all, A part, we will assume D sine theta equal to lambda. In terms of lambda we have to assume, okay, D sine theta we have to assume lambda. Now we have to divide the slit into two parts. AB we have to divide into two parts. What are that two parts? We can name AP and BP. So we have to take first wavelet from upper half and second wavelet from lower half, and after that it will superimpose here at the point P1. So we have to find out now, are they traveling equal distance? So no, AP and BP, if we meet them at the center, we saw that AP and BP1 means AO and BO were same. But here upper half and lower half, if they travel that side inclined, so there is the part difference present other than 0. So like between A and B last point, the part difference is D sine theta. And if we take the one wavefront from the upper half and one wavefront from the lower half, then the effective part difference is only this line. Okay, you can see that between this wave and this wave, what is the effective path difference? It is just this line. And according to the property of the triangle, that if one side is D sine theta and we join the midpoints of these two sides, then this line joining is just half of this line. According to that logic, this line value will come D sine theta by 2. Thus the effective path difference between the two wavelets from upper half and lower half is now D sine theta by 2. But we have assumed already D sine theta equal to lambda. So D sine theta by 2 will be lambda by 2. So this line is written. Thus the effective path difference between the wavelets from AP and BP is D sine theta by 2. But D sine theta we have assumed lambda. So D sine theta by 2 means lambda by 2. Now what is the meaning of lambda by 2 path difference reaching there? Will we get minima or maxima? Let us understand it. Students, whenever we say that path difference is lambda by 2, so path difference of lambda by 2 is its meaning is pi phase difference. Remember this point. Lambda by 2 path difference means pi phase difference between the two waves. So the meaning is, if the wavelet reaching from the upper part is this way reaching at the point P, then wavelet reaching from the lower part is at pi phase difference. Pi phase difference means just opposite. So that's why what happens, the wavelet from the upper half and wavelet from the lower half of this side, they cancel each other. Cancel means no intensity at the P1 will be left. That's why we will get here minima. Okay, so this way the resultant is minima. In the same manner, let us assume another value of D sine theta. So now we have to take D sine theta value what? 3 lambda by 2. Okay. We have to assume the increasing order of lambda by 2, lambda by 2. So if it is lambda, it should be 3 lambda by 2. Next value. Then next value should be 2 lambda. So for all these values, we will get minima, maxima answer. Then we will generalize it. So Now the slit AB, in this case, we have to divide into 3 parts. Okay, so if I draw the diagram here, this slit AB, we have to divide into 3 equal parts. The superposition will be done from in between the wavelets from this first part, second part and third part. They will reach at point P1 now. Okay, and each of the wavelet with respect to each other is at how much effective path difference. So now, because we have divided we have divided the slit into 3 parts. So this path difference we have to divide by 3 now. So effective path difference between each of the wavelet with respect to each other is again lambda by 2. That means pi phase difference. So now what will happen on this P1? From this first part of the AB slit, the wave will come like this. From the second part of the slit, the wave will be at pi phase difference. That means this. And from this third part of the slit, with respect to second, it will be at pi phase difference. Yani first का उल्टा second, second का उल्टा third. You can see now we will get maxima or minima. Just find out. So you can see that 2 parts are equal and opposite. They will cancel, but 1 part will remain. Okay, that means the intensity of light from 1/3 of the slit will remain on the screen. That means we will get maxima. Okay, so let us write language for this part. So dividing the slit AB into 3 parts now, effective path difference between the wavelets from the 3 parts is only lambda by 2. You can see it is obtained by this. Wavelets from 2 parts cancel each other and wavelet from the third part makes intensity on the screen. So we get the maxima. Okay, so we have done lambda and 3 lambda by 2. Now note down this case. We are moving to 2 lambda. D sin theta equal to 2 lambda. Let us do the C case. Okay, D sin theta lambda we have assumed. 3 lambda by 2 we have assumed. Now 2 lambda. So in this case, divide the slit into 4 parts. Okay, 4 equal parts. Like if I show you here, AB slit is this. So 1, 2, you can see 1, 2, 3, 4 equal parts we have divided. Now, what is the effective path difference between the wavelets? So whatever is total divided by 4. Okay, so D sin theta, which is 2 lambda now, we have to divide it by 4 because we have divided. ये पार्ट डिफरेंस है टोटल का और हमें 1/4 का चाहिए. तो कितना होगा? D sin theta by 4 कितना हो गया? लैम्डा बाय 2. तो ईच वेवलेट्स के बीच में पार्ट डिफरेंस कितना है? लैम्डा बाय 2. सो इफेक्टिव पार्ट डिफरेंस बिटवीन द वेवलेट्स इज लैम्डा बाय 2, बट देयर आर 4 सच पार्ट्स. सो दैट मीन्स लैम्डा बाय 2 मीन्स पाई फेज डिफरेंस. ओके, सो सबसे ऊपर वाले से वेव ऐसे आएगी स्क्रीन पे, फिर दूसरे वाले से आएगी जस्ट अपोजिट क्योंकि पाई का फेज डिफरेंस है. थर्ड वाला जो होगा वो सेकंड के अपोजिट होगा और फोर्थ होगा वो थर्ड के अपोजिट होगा. यानी फाइनली ये होगा कि एक दूसरे के अपोजिट है. फाइनली 4 पार्ट्स हैं, सबने कैंसिल कर दिया. सो नो इंटेंसिटी मीन्स वी विल गेट मिनिमा. ओके, सो जब जब लैम्डा 2 लैम्डा ये वैल्यूज आ रही हैं तो मिनिमा आ रहा है. नाउ लेट अस डू दिस 5 लैम्डा बाय 2 केस नेक्स्ट. ओके, नाउ डिवाइड द स्लिट ए बी इंटू 5 पार्ट्स. ओके, इफेक्टिव पार्ट डिफरेंस निकालते हैं. डी साइन थीटा इक्वल टू 5 लैम्डा बाय 2 है, इसको 5 से डिवाइड किया. 5 पार्ट्स है इसलिए आंसर क्या आया? लैम्डा बाय 2. सो इन ईच केस इफेक्टिव पार्ट डिफरेंस विल कम लैम्डा बाय 2 ओनली. दैट मीन्स पाई फेज डिफरेंस. सो effective part difference between the wavelets from 5 parts is lambda by 2. How they will reach on the screen? So if this is AB slit, 1, 2, 3, 4. So 5 parts have become. सबसे ऊपर वाले से वेव ऐसे पहुंचेगी, सेकेंड वाले से वेव होगी फर्स्ट के अपोजिट यानी लैम्डा बाय 2 पे, फिर थर्ड वाली वेव होगी सेकेंड के अपोजिट, फिर फोर्थ वाली वेव होगी थर्ड के अपोजिट और फिफ्थ होगी फोर्थ के अपोजिट. फाइनली यू कैन सी 4 waves will cancel each other, only 1/5 will remain. So 4 parts cancel, wavelet from fifth part makes intensity on screen, so we get maxima. So this way we have discussed the conditions of maximas and minimas for different values of d sine theta. Now let us generalize the formula in the next sheet. Note down these conditions of secondary maximas and minimas. As you have seen that d sine theta, whenever it is lambda, 2 lambda, that means n lambda in general, we get minima, and whenever d sine theta is odd lambda by 2, okay, or odd means 2n plus 1 lambda by 2, then we are getting the secondary maximas. So these are the conditions of secondary minima and maxima. Keep the condition of central maxima separate, where the path difference is coming 0. Okay, and also notice carefully the conditions which are obtained in terms of d sine theta, that are just opposite to interference conditions. In interference, whenever n lambda path difference was there, we were getting maxima, but here n lambda we are getting minima. Okay, so keep this difference clear. So this is to be done whenever conditions of maximas and minimas are asked. Okay.